Welcome to this video about variance explained in regression models. We'll begin by revisiting the concept of variance. Variance tells us how spread out or dispersed our data points are around the mean. Variance is usually denoted by the Greek symbol sigma squared. Variables with a higher variance are more spread out. In the figure on the bottom, I've got 3 example variables with different variances. The black lines on each of these variables represents the mean of each of these 3 variables. The first variable x has the largest variance, which is 100, and as you can see, the data points are far more spread out around the mean, whereas on the right, all of the data points are relatively concentrated around the mean. And indeed, this variable has the smallest variance. So variables with the higher variance are more dispersed or spread out around the mean. The standard deviation is defined as a square root of the variance. Normally in applied settings, when we talk about variance, we've collected some data, such as shown here on the left, and we want to know how spread out our numbers are. We can call this the sample variance. However, the concept of variance can also be applied to describe random probability distributions. So for example, here on the right, we have the normal probability distribution shown. Probability distributions also have variances. However, the procedure for calculating these is a little different, and we won't cover it in this video. Next, I'll provide a step-by-step guide on how to work out the sample variance. In this example, we have a variable y that we will work out the variance for. In this example, y is composed of 6 numbers, shown in this column here. First, we need to work out the mean of y, which is 4. In this middle column, we will then take each value of y and minus the mean. For example, 6 minus 4 is 2, or 1 minus 4 is minus 3. This second column here now tells us each observation's deviation from the sample mean. After this, in the third column, we square each observation. So minus 3 times by minus 3 is positive 9. Now these squared deviations from the mean tell us how much each observation deviates from the mean, regardless of whether it deviates in a positive or negative direction. Now we have 2 final steps. First, we will add up everything in this final column here. So 4 plus 0 plus 1 plus 9 plus 9 plus 9 is 32. Next, we divide this number by the number of observations we have, minus 1. So here we have 6 observations, or 6 rows of data. So we'll divide 32 by 6 minus 1. So 32 divided by 5 is 6.4. And here we have our estimate of the sample variance. To summarize, we look at each data point, we work out how much each data point deviates from the mean, we square these deviations, we add them up, and divide them by the number of observations minus 1. If you've watched my previous video in regression, this procedure for working out the variance should be vaguely familiar to the procedure we use to work out the error sums of squares. Let's say we fit an ordinary least squares regression model to the outcome y, but we don't have any predictor variables other than the intercept. Our formula would then look a bit like this. On the left, we have our outcome y, and this is equal to an intercept, which is a fixed constant, plus some random error. In ordinary least squares regression, our aim is to find the value of the intercept that minimizes the error sums of squares. In the context of regression, the errors refer to the difference between these observed values here and the predicted values from the regression, which is shown on the black line here. The length of these red bars here indicate the size of the error of each observation. The regression intercept will be the value that is closest to the observed data points. It just happens that the least squares intercept will be the mean of y in this example. And this is because the mean is also the value of the intercept that minimizes the error sums of squares. Or the mean is the value of the intercept that is closest to all these observations. So our regression model with just the intercept will look like the following. Again, you should watch our previous video in regression to understand these tables a little better. On the left column, we have our outcome variable y again. Because we have an intercept and no predictors in our model, this column here with predictors left blank, and because the intercept in this case is 4, our regression model is predicting that the value of the outcome for all of these observations should be 4. The next column, error, represents the difference between the observed values y and our model predicted values 4. And again, we can square these error terms on the right here so that these negative values, such as -3, become positive. In the context of regression, we defined in a previous video this term called the error sums of squares, and we find this error sums of squares by squaring the error terms and summing across them, which again gives us 32. So hopefully you've noticed that this error sums of squares looks a lot like the top half of our variance formula that we saw earlier. Previously, when we were working out the variance, we squared the deviation of each of these values from the mean, and that gave us 32. And in the regression model, when we just have an intercept, we're essentially doing the same thing here. So the variance y is equal to the error sums of squares from our regression model when we just have an intercept, divided by n-1. Now we can move on to the topic of this video, which is the variance explained. The variance explained is a property of a regression model with one or more predictors. It measures how strongly the predictor variables are associated with the outcome variable. The variance explained is usually denoted by the symbol r² here, although it's also known as the coefficient of determination, or just simply r². There are a few different formulas for working out r², which will give you the same result. Here we're going to focus on this one, which uses the error sums of squares. On the bottom of this ratio, we have the error sums of squares of a regression model with just the intercept. And on the top of this division, we have the error sums of squares of the regression model that we want to calculate r² for. If the predictor variables in this model here are related to the outcome variable, we would expect that the error sums of squares should be significantly reduced in this model relative to a model where we just have the intercept. In other words, this model's predictions should be significantly more accurate and the errors should be lower. That should then lead to a higher measure of r² or variance explained. Let's see how this works visually. On this slide, we're working out the variance explained for the regression model shown on the right, where we have a single predictor x. The black line here is our regression line. It shows the regression model's predicted value of y at different values of x. So for example, when x is equal to 2, our regression model would predict that the outcome y should have a value of about 2.75. To work out the variance explained, we first estimate the error sums of squares for the regression model with just an intercept, which we did by hand earlier over here. We can then compare these error sums of squares to the regression model, which includes all the predictors that we're interested in. So in this example, we have a single predictor, but you could have multiple predictors in this model. As you can see on the right, when we include the variable x as a predictor, the regression model's predictions are far closer to the observed outcomes. And this means that the error sums of squares is now much smaller. So if we take the error sums of squares for the model that we want to calculate r² for, and divide it by the error sums of squares for the regression model with just an intercept, we can see in this example that these error sums of squares are 8.8% of the size of these sums of squares. In other words, 2.83 is 8.8% of 32. This shows that the error sums of squares have decreased by really quite a bit. To work out the variance explained, the final step is to take the value of 1 and minus it from this ratio. And this gives us a value of 91.2%. So including predictors in this model here decreases these error sums of squares by 91.2%. In other words, our predictors explain 91.2% of the variance in the outcome. Although in this example we have a single predictor, you can in principle have many more predictors. To recap, R² is a measure of how much variance your predictor variables explain in an outcome variable. We calculate it by comparing the error sums of squares of your regression model relative to a regression model with just the intercept and no other predictors. If your predictors are good at explaining the outcome, we would expect that these error sums of squares to decrease, and therefore the value of R² will increase. When calculating variance explained in a standard ordinary least squares regression analysis where you have a single sample, R² must be between 0% and 100%, where 0% indicates that the predictors explain no variance in the outcome, and 100% indicates that your predictors explain all the variance in the outcome. There are certain situations where you can have negative explained variance, for example when using cross-validation. One problem with the standard measure of R² or variance explained is that it's slightly biased. When we fit a regression model in a sample of data, our predictor variables will always explain some variance in our sample, even if at the population level there is no relationship between our predictor variables and our outcome. To demonstrate on this slide, I've randomly simulated two completely independent variables x and y. I've ran this simulation 10 times and calculated the R² for the regression model predicting y from x in each of these simulations. Unless your sample is infinitely large, adding a predictor to your regression model will always reduce the error sums of squares in some way. And this is a problem sometimes termed overfitting. One way we can get around this is by fitting our regression model in one dataset and testing to see how well it explains variance in another dataset. This approach is called cross-validation. Another way we can adjust for this bias is using a kind of fancy formula, which is called the adjusted R² measure. The adjusted R² is a better measure of variance explained, although in large samples it is very similar to R². On this slide we have some simulated data, but instead of reporting the R², I've reported the adjusted R² in each sample. These adjusted R² remove the bias associated with the standard R². In this case here, if we average across these simulations, the average adjusted R² is now closer to 0. And that's what we would expect, given that I know there's no relationship between x and y because I've simulated the data myself. When you run your regression model in R, you will see that the R² metric is usually reported here at the bottom. In this case, the difference between the standard R² measure here on the left and the adjusted R² measure on the right is relatively small. The square root of the variance explained is sometimes termed the multiple correlation coefficient. There isn't really much advantage to reporting this relative to the standard R² measure. One interesting thing about the multiple correlation coefficient, however, is that when you run a regression model with a single predictor variable, the multiple correlation coefficient is equivalent to Pearson's correlation coefficient. So in our previous model, the multiple R² was 0.42. If we take the square root of 0.42, we get 0.654. And here we can see on the left that our correlation estimate is exactly the same, give or take some rounding error. This is just to emphasize that correlation analysis shares a lot of similarities to regression analysis.